My name is Malcolm Smith. For my sins, I'm chairman of the Noise and Vibration Engineering Committee. I'm giving a talk on active noise control, applications of, and this is actually not one of my specialist topics. I have done active noise control, but it's mainly my colleagues Simon Roberts and Gergo Oroz who do most of the work in the consultancy unit at ISVR on active control. And then also I've included some material. I've said thanks at the end here to Phil Nelson, Steve Elliott, and who are the leaders in active control over the years, and they've sent me materials. And also I've got a slide from Mike Lower, who is a noise at work person actually. So the essence of the talk is that active control has been around for quite a long time, and it's growing in capability all the time. And the question is, what's the potential applications to noise control at work, which is what we're all here for. Just a few historical things. Anybody who came on the advanced course in noise and vibration control at Southampton at ISVR years ago would have been had a trip round in the Lotus motor car, which was an early demonstrator for active noise control. And then a lot of the work that's gone on historically was in control of propeller noise. This is a much more recent control project, one of Simon Roberts' Chinese projects. This is a Chinese high-speed train where they're using active control in the first-class cabin to control to just make it slightly more luxurious. And then the Fiat is here because that was part of what was called the Green City Car project, I think, which was a Steve Elliott project. So there's all of these examples around, and just to give you one quick picture of the capabilities of active noise control in aircraft, in propellers aircraft. There's a noise simulator in ISVR which generates these sorts of pictures. Basically, you can knock, I think it's about 10 decibels off the sound of the propellers inside the aircraft cabin. This was a multi-channel digital controller with 48 actuators and 72 sensors, it says, distributed through the cabin. And actually the Q400, the Bombardier Q400, is probably an aircraft that many of you will have flown on. Flybe use quite a few of those, and so you'll all have experienced active control. The principle of active control, I'm sure you're all familiar with, is you create an anti-sound wave, something which is out of phase with the original signal, both temporarily and preferably spatially. And the essence of active control is the wider you can do it spatially, the more useful it's likely to be for you. And so the original example was developed in 1936, which was sound propagation down a duct. You won't be duct acousticians, most of you, I'm sure, but at low frequencies only the plane wave propagates down a duct, and so you can use a single microphone and a single loudspeaker to actually get very good sound reductions out of an active control system. And that it works because you've effectively constrained the sound field to a single degree of freedom, which is just this plane wave mode going down the duct at low frequencies. So there's a nice example on the HSE website of this, a pneumatic transport system where there's a centrifugal fan acting as used to convey material around production lines. And you can potentially install a set of active control loudspeakers and control microphone, an error microphone into the system and control the noise there. Of course, you could use noise control at source of the fan, but there's different circumstances where you want to use each of them. So that's one good industrial example. And so I thought before I went on, I should just give a little bit of summary of terminology for active noise control, which is that there's feed-forward control, which is where you've got a reference signal close to the source, and you use that as a reference for your secondary actuator. And so a good reference is actually a tacho signal off an engine or something like that, and all you need is that reference is correlated to the source, especially if it's tonal noise. It doesn't work so well if you've got broadband noise. In my view, you also need a relatively stable transfer function from the reference signal to the control point. Actually, Simon Roberts is the expert, and he said that's not necessarily the case, but I'll skate over that a little bit. We also had some debate between us about which of the many systems around are feed forward and which are feed back. And there was considerable debate about that as well, in fact. Simon's view was that almost all systems are feed forward because it's by far the most effective system if you can get a good tacho signal. Gergo actually gave me a very interesting response. I said, surely active headphones, which I'm coming on to a minute, are feed forward. You've got a microphone on the outside of the helmet and they control sound transmission through. His response was, actually you have hybrid systems which do have an external microphone for feed forward but also have an internal microphone for feedback control. So you can make the systems as complex as you like. And then you've obviously got single channel systems like the duct acoustics problems, or multi-channel systems like the aircraft control systems. So there is this issue about active control, about where are you going to get control, and getting global control is impossible. You cannot have a sound source sitting in free field and get control around 360 degrees. It just doesn't work like that, or very difficult to get it to work like that. So it works best when you've got a closed space like a motor car here, where you might have a tacho signal coming off the engine and a number of microphones and sensors around the space. Or you might go for local control, where you've got a microphone near the ear and you try and control the sound field near that microphone, and then that creates a zone of silence around. The trouble is that the effective zone of silence, Gergo actually put it as being only 1/10 of a wavelength. I might have gone for 1/4 of a wavelength myself, but it is actually quite a small zone of silence that you can create. And so this means that active systems are definitely used for low frequencies and used to complement passive control systems that work at higher frequencies. The great advantage, therefore, and so that's what this graph on the left shows, on the right, sorry, that you've got active control at low frequencies and passive control at high frequencies. So the great advantage of active control is that to get good low frequency performance, you need massive systems, either large silencers or heavy constructions, things like this, whereas active control systems can generally be much lighter. The difficulty is where are you going to get control, and this is a picture that Gergo had in one of his presentations, that if you've got a single secondary source, then you can control 1 degree of freedom and get good attenuation, good noise reduction for a single low frequency mode of a room, let's say. And if you want to get, but that doesn't provide control at higher frequencies. If you want to get good global control, then you need many secondary sources to make it work. And so that's why just repeating ANC is effectively a low frequency technique. So by far the most successful example of active noise control is actually active headphones. And I did just wonder how many people in the room have a set of active headphones? That's probably sort of 4 or 5 of you, 5 or 6, which just shows the success of getting them out into the market. And there's it was interesting when I looked this up, what the applications are. One is noise reduction for travellers, which was the original application, reducing aircraft noise. But you might want to suppress the television while you're listening to the music. You know, wife's listening to the telly, you're listening to the music. Noise reduction at the gym. Gyms are very noisy places with people pounding away on their running machines and the radio blaring away in the corner. Not very pleasant at all. And then blocking out snoring as well was an application. But the trouble with the snoring application is that it's the listener who's having to block out the snoring and not the person who's doing the snoring. And so I'll come back to that in a moment. In terms of noise at work, this is a picture of my colleague Mike Lower, who likes to keep himself very discreet, as you can see. And so one of the original noise applications of active noise control at work was flying helmets. And the table, we don't have time to go into, does show that he was getting 5 decibels of noise reduction out of this system. But the main consequence, actually the noise levels are only about 70 decibels, but the benefit of the noise reduction was that you could turn down the level of the communication systems. So whereas the communication systems were up at 85 or 90 dB before the control system went in, they could be dramatically reduced after the control system went in. This is another picture from the HSE website, which I think was probably produced by Steve Elliott. There's an acknowledgement for Steve Elliott in there, showing how the automotive industry, active control of engine noise is now a well-established technique in the automotive industry, and you'd be astonished the number of car models that do have some sort of active control in them. And the big thing at the moment is research into control of road noise, which is a broadband input transmitted through the suspension system, and so that's a much trickier system to make work. So the main thing that I wanted to bring out in this talk was that there's clear application for these things, for noise in cabs and industrial machinery and things like this. The techniques are not new, the hardware is available. It's simply a question of the cost of implementing systems and making them reliable. And then finally, this is the one example which is my own work, which was active control of structure-borne noise. Pumps are often a source of structure-borne noise and vibration. And so we did a very nice project where we took a 2-stage isolation system. The green bits are isolators and the blue bits are isolators. And the red bit are dynamic shakers controlling the floating mass of the isolation system. And that was what you're looking for here is 2-stage isolation systems are already very effective, but we got another 25 dB of reduction at the rotational speeds of the pumps just by effectively holding that floating platform steady and stopping it moving. And so the application I could see for this is sort of avoiding sound transmission on offshore platforms, stuff that causes sleep disturbance in the sleeping quarters and things like this. You're not necessarily going to be doing this for avoiding high levels of noise, but for just blocking out the transmission of low frequency noise. The essence of it is that there's a restriction in the transmission path where you have to go through the isolators, and therefore you've got effectively 3 or 4 degrees of freedom in here, which you can control quite easily. So just a touch on cases where active control won't work, and actually the snoring problem, somebody did ask us about the snoring problem, and we decided it was essentially a non-starter. That didn't stop somebody trying, I think it was one of these sort of web-based funding things to try and get something, and they've got a very unacceptable looking active control device attached to the snorer now rather than to the listener, but I think that never really got off the ground. Another slightly oddball example that I had as manager of the group was somebody had a very expensive property just near a waterfall on the River Thames and wanted to know whether he could block out sound from the waterfall, which was disturbing his dinner parties. And we didn't take that job on either. This is my last slide, conclusions. Active control is definitely worth considering as an option, but it's not a panacea. It works at low frequencies and it complements the performance of passive treatments at higher frequencies. So the applications that I can see for it in the noise at work scenario is definitely local or global control inside control rooms, and then some potential for local control at workstations around machines, just creating a quiet space that you can move into rather than a hood. Definitely noise control in ducts, intakes and exhaust ducts. And then I think control of structure-borne noise on various sorts of platforms and so on is probably a good application as well.